There are these creatures that came from off-world. These are outsiders. NASA, famous for its historic revelations, has lately uncovered that this new planet isn't simply captivating because of its size and area, but additionally because it shows lights that give off an impression of being counterfeit. Are we very nearly revealing secrets that could change our comprehension of the universe? Could this revelation mean there is life on other planets? Join us as we explore NASA's intriguing discoveries and uncover the reality about these phenomenal lights. In 2007, NASA sent off the Dawn rocket with a mission to investigate some of the most interesting objects in our planetary group. Dawn was remarkably equipped with 3 ion motors, allowing it to embrace an exceptional journey. Dawn's journey began with a 14-month study of Vesta, the second-largest asteroid in the belt. During this time, Dawn sent back detailed pictures and data revealing Vesta's complex surface and various land histories. After completing its mission at Vesta, Dawn set out on the second and perhaps most interesting part of its venture, a detailed investigation of the dwarf planet Ceres. Due to its ion motors, Dawn was able to leave Vesta's orbit and set out to reach Ceres, an accomplishment that traditional chemical propulsion would have found testing. These motors provided a constant, gentle push, allowing Dawn to travel vast distances efficiently and enter a stable orbit around Ceres. Discovered in 1801 by Italian cosmologist Giuseppe Piazzi, Ceres is the largest object in the asteroid belt between Mars and Jupiter. For many years, it was viewed as the smallest dwarf planet in our solar system until its renaming in 2006. With a diameter of around 950 kilometers, Ceres is the largest and most massive body in the asteroid belt and one of the most captivating due to its interesting attributes. As Dawn moved towards Ceres, researchers eagerly anticipated the first detailed pictures of this baffling world. They found bright spots dissipated across its surface, most notably in a huge pit now known as a crater. These bright spots ignited quick interest and speculation within established researchers. Before Dawn's mission, the best image we had of Ceres was a fuzzy, low-resolution picture taken by the Hubble Space Telescope. Researchers knew very little about this dwarf planet, and the prospect of finally getting a close-up view was exciting. What mysteries would Ceres uncover? What new discoveries awaited? The mission promised to improve our understanding of the planetary system's development and the role of water in shaping planetary bodies. The bright spots on Ceres are unlike anything seen on other asteroids. They appear to be made of highly reflective material, possibly salts left behind by sublimated water. This observation alluded to the chance of cryovolcanism on Ceres, a process where volatiles emit with water or briny fluid instead of liquid rock. However, what precisely are these strange lights, and what do they reveal about the nature of Ceres? Could they be proof of ongoing geological activity or something significantly rarer? Ceres stands out from other celestial bodies in the asteroid belt due to its size, mass, exceptional composition, and potential for water and ice. Unlike typical rocky asteroids, Ceres has a composition more akin to a comet, suggesting it holds more secrets about the early solar system than we ever envisioned. Following 2 years on the way, the Dawn rocket finally began its approach to Ceres in mid-2015. This moment marked a significant achievement in the mission as Dawn prepared to deliver humanity's most memorable close-up perspectives on the largest object in the asteroid belt. As Dawn moved closer, the pictures of Ceres became increasingly detailed, offering brief looks at a world that had previously been shrouded in mystery. The first pictures revealed a surface dotted with craters, indicative of a long history of impacts. However, it wasn't simply the cavities that captured the attention of researchers and space enthusiasts alike. Among these features were the baffling bright spots that strikingly contrasted with the darker rocky landscape. As the pictures continued to improve in resolution, mainstream researchers buzzed with speculation about the nature of these bright spots. Were they ice patches reflecting sunlight, or could they be something significantly more fascinating? Hypotheses ranged from mineral deposits to potential indications of cryovolcanic activity. Surprisingly, closer examination revealed that the most brilliant spot was not a singular substance, but rather a group of several distinct spots. This discovery only deepened the mystery, and the speculation that these were deposits of salts left behind by sublimating water gained traction. This would suggest that Ceres had, or still has, some form of geological activity capable of bringing water or briny fluids to the surface, where they rapidly dissipate, leaving bright reflective deposits. These discoveries challenged existing ideas about Ceres, portraying a more unique and complex world than previously imagined. The presence of such features hinted at the possibility of subsurface water or briny pockets, which could have significant implications for how we interpret the potential for life in our solar system. Yet, what makes Ceres unique among other celestial bodies? Ceres is an intriguing planet often described as an icy world with a rocky yet permeable surface. Unlike most asteroids in the belt, which are principally made of rocks and metals, Ceres stands out due to its unique arrangement. Its surface is a mix of water ice and hydrated minerals, including clays and carbonates, which give it a distinct, less dense structure compared to its neighbors. This composition suggests that Ceres has a significant amount of water. The surface layer is rocky yet permeable, with ice and other volatiles trapped inside. This icy characteristic is more reminiscent of a comet than a typical asteroid, indicating a history that could involve a mix of rocky and icy materials. Digging deeper beneath its surface, Ceres reveals many more interesting aspects of its composition. The dwarf planet is believed to have a differentiated interior comprising a muddy mantle and a core. The mantle is thought to be rich in water ice, accounting for roughly half of Ceres' total volume. This mantle, a blend of rock and saline solution, surrounds a core that could be made of denser material, perhaps silicates. The presence of such a large amount of water ice suggests that Ceres might have once harbored liquid water, particularly if its core was warmed by radioactive decay early in its history. This internal structure sets Ceres apart from its asteroid neighbors and also raises intriguing questions about its potential for geological activity and the role of water in its evolution. However, that is not all. The discovery of ammonia clays on Ceres implies that the dwarf planet may have formed in a colder part of the solar system and migrated inward. The presence of ammonia can lower the freezing point of water, supporting the existence of subsurface brines. These insights into Ceres' composition and history not only enhance our understanding of this fascinating dwarf planet, but also provide valuable clues about the processes that govern the formation and evolution of icy bodies throughout the solar system. Cryovolcanism is a captivating and somewhat obscure geological process, especially when contrasted with the more familiar volcanic activity we see on Earth. Unlike traditional volcanoes that eject liquid rock, cryovolcanoes, also known as ice volcanoes, emit volatiles such as water, ammonia, or methane. These substances can exist as liquids or gases in the supercold conditions where cryovolcanoes are found on Ceres. The cryovolcano operates by allowing water loaded with dissolved salts to reach the surface. When this salty water interacts with the vacuum of space, it rapidly sublimates, changing directly from a solid or liquid state to gas. This process leaves behind bright, reflective salt deposits. The most famous of these bright spots is located in a crater named Decatur, also known as Spot 5. This region has earned significant attention due to its high reflectivity and occasional mists observed by the Dawn spacecraft. These mists are believed to be caused by the sublimation of water, suggesting that cryovolcanic activity could still be ongoing or has occurred relatively recently. In addition to Spot 5, Ceres has several other bright spots, each with its own unique characteristics. These spots are not limited to a single region but are dispersed across the dwarf planet's surface, indicating that cryovolcanism might be a widespread phenomenon on Ceres. The presence of these bright spots highlights the unique nature of Ceres and raises significant questions about the potential for life in our solar system. The dynamic and active nature of Ceres challenges past assumptions that it was a geologically dead world. As the Dawn spacecraft provided more detailed images of Ceres, an abundance of surface features began to emerge. The outer layer of Ceres is dotted with a variety of craters, each telling a story of the dwarf planet's history. Some craters are relatively shallow and eroded, indicating an old surface that has been subjected to various impacts over billions of years. Others are more well-preserved, with sharp edges and deep basins, suggesting more recent impacts. Interestingly, the number of craters on Ceres is less than initially anticipated. This discrepancy hints at geological processes that may be renewing the surface and erasing evidence of older impacts. One hypothesis is that Ceres' icy composition allows for a form of cryovolcanic resurfacing, where subsurface materials intermittently well up and cover old features. This ongoing geological activity suggests that Ceres is not a static world but one that has been, and potentially still is, actively evolving. Additional evidence of geological activity on Ceres comes from the observation of cracks, grooves, and box-like structures on its surface. These features indicate that the crust of Ceres has experienced significant stress and deformation. Some of the cracks appear relatively young, possibly only a couple hundred million years old, suggesting that the crust is still dynamic. The grooves and boxes on Ceres likely formed as the crust was stretched and pulled apart, while ridges of mountains and compression features show areas where the outer layer was pushed together. These contrasting features offer a glimpse into the complex processes that have shaped Ceres over time. The presence of a large dome-shaped mountain in one of the craters suggests the possibility of internal pressure or upwelling of materials, possibly related to cryovolcanism. This feature, along with the extensive network of cracks and depressions, points to an active and evolving surface. The Dawn mission's observations have also uncovered intriguing surface compositions beyond the bright spots and reflective salts. NASA's data has revealed a range of surface materials that are critical for understanding Ceres' geological history. For example, certain regions on Ceres show a dark, fine-grained material that stands out sharply from the brighter salt deposits. This darker material is believed to be a type of carbon-rich substance, possibly organic, which adds another layer of complexity to Ceres' composition and suggests the potential for prebiotic chemistry. The interaction between these materials and the icy surface may play a role in the chemical processes occurring on Ceres. In addition, the detection of organic compounds on Ceres has sparked significant interest in astrobiology. Organic molecules, which are the building blocks of life as we know it, have been found as carbon-rich compounds. These discoveries are particularly exciting because they suggest that Ceres could have conditions suitable for the formation of more complex organic molecules. The presence of these compounds opens up possibilities regarding the potential for life, or at least the building blocks for life, being present on this dwarf planet. Another notable feature is the vast number of mysterious dome-shaped structures on Ceres. These domes, some reaching heights of up to 6 kilometers, are believed to be the result of subsurface processes pushing up material through the crust. Their shapes and sizes suggest that they may have formed from cryovolcanic activity or from internal pressure driving materials upwards. Understanding these formations is essential for unraveling the geological history of Ceres and its internal dynamics. Moreover, the gravity data collected by Dawn has provided insights into the internal density distribution of Ceres. Variations in gravity reveal the presence of differing layers within the dwarf planet, indicating that Ceres' interior may have complex structures, including a potential subsurface ocean or briny pockets. These discoveries are crucial for understanding the thermal history of Ceres and its capacity to harbor conditions conducive to life. Overall, the Dawn mission has not only expanded our knowledge of Ceres, but also transformed our understanding of small celestial bodies in the solar system. As more data is analyzed, researchers hope to further unravel the mysteries of this intriguing world and its potential to shed light on the broader processes that govern planetary formation and evolution. Ceres continues to captivate scientists, offering a treasure trove of geological and chemical insights. The combination of its icy surface and rocky mantle presents a unique opportunity to study processes that might have shaped early planetary bodies in the solar system. Additionally, the study of Ceres may provide valuable lessons about the evolution of similar dwarf planets and icy moons, such as Europa and Enceladus, which also harbor subsurface oceans. Investigations into Ceres' surface composition have revealed a diverse array of minerals, including carbonates and clays, which suggest a complex geological history influenced by water activity. Researchers are particularly interested in how these minerals interact with one another, as such interactions could hint at past environmental conditions that might have been suitable for life. The potential for future missions to Ceres is also a topic of discussion among scientists. Follow-up missions could explore the subsurface more thoroughly, possibly drilling into the crust to analyze deeper layers. Understanding how Ceres fits into the broader context of planetary formation and evolution could have profound implications for our search for extraterrestrial life and the origins of water in the solar system. As our technological capabilities advance, the prospect of uncovering more secrets from this enigmatic world becomes ever more tantalizing.